Okay, now we're ready. So, oh, I'm just gonna mute you here. Oh, there you go. Nice. All right. And we're still recording. Okay, next. So just heads up, right? I gave you a table that we're gonna use. Now I hate tables. We use tables, but in a test, right? What are you supposed to use? Well, I mean, you'll see what they're for later. Hopefully today, maybe tomorrow. But we use them to find probabilities. And so we're not, I don't know, calculus geniuses. So we use tables. So we need something for the tests, right? Because we won't have software. But in general, we should be using software. So I am going to show you how to use R to find the probabilities. And I am going to be using, well, it's called Posit now, Posit Cloud. It used to be RStudio Cloud, which you would have to sign up for a free account, but then you can just use it. And instead of installing things on your laptop, right, that's kind of annoying, then you can use it on your iPad, for example. And it's just kind of a nice, it's already up and running, and we can just jump in and use it right away. But if you're familiar with RStudio, right, it just looks like a cloud version of RStudio. So we can just jump right in. And so I've got a couple of commands, and I did post this R script on Moodle, but like I said, we'll kind of do that once we get there. Yeah.
Yeah, so will we be using R in this class?
Yeah, I want to do a little bit. We won't have time to do a whole lot, right? But it's so important that you understand that we should be using software for this stuff, right? And so I think it's good to kind of sneak a little bit in there when we can, right? And so, yeah, that's what I want to show you. But I also wanted to give you a heads up that I am using RStudio Cloud, or I guess Posit Cloud. They did a huge rebrand. But it's all the same. So if you wanted to sign up for an account, it's free. So my main complaint is that it's very slow. So if you want it faster, then you can download a local copy. But all right, so that was one thing. Okay. I also just handed out a formula sheet. I think if I had to hand it, so my fear is if I hand this out on the first day of classes, everyone would just walk out. So no, thank you. I don't want this. But for us, now that we've made kind of a dent already, right? If you're looking at your formula sheet, well, I guess we've done these first two blocks, right, of formulas. And that's how we're going to keep working through. So today we're going to work through this block, right? And then next week we work through the next block. And so they'll be in order. And I just kind of newspaper style go like this and then on to the next page like this. Okay. So these are the formulas that you'll have. The formula sheets you got today are yours to keep forever, or however long you want to. But if you ever need a fresh one, I'll have fresh ones as well. Okay, so I gave you a formula sheet, and I also gave you a t-table, it's called. And it looks like this. And until we've talked about kind of the normal distribution, this won't make a lot of sense, but once we have, it will. Okay, so there used to be another table, a bigger table that we used. And this is my first term that I'm saying, no, I'm not going to use that one. I'm just going to use one table. One table is plenty. And then we'll use software for the rest. Okay. One kind of mega thing, I guess. Tomorrow's class had something come up, so I will only be able to do it on Zoom. Right, I'll still post the video afterwards if you know you can't log on to Zoom or whatever because maybe you're on campus, and I am sorry about that. but, oh, that's not us, is it? Nope, nope, nope. But tomorrow is on Zoom only. Let's see here. Step 2:30. Let's see here. Oops. Let's make this a little bit bigger. Okay. I need to make it very, very clear. I want you showing up for no reason. Well, I guess you could always come in here and join Zoom, but I won't be able to be here. Okay, so tomorrow on Zoom only. And you guys have been pretty good about taking advantage of that. I know there's some people on Zoom right now, so that's good. And the Zoom link is just on our Moodle page. It's at the top here. I always use this. So I use this is just my Zoom room and I just use it for everything. Right, so the Zoom classroom link, or if you prefer the meeting ID, it's there too. Okay. I guess, how can I? 783. So it used to be my phone number, but that was for my personal account. And then when I made a school account, it gave me a random number. So now I never remember it. Oops, that's not what, boy. Oh my gosh. Hey. Yeah, I don't have that many games on here, but I've got some. Probably Sudoku or something. Let's see here. Meeting ID is what I wanted to. 783. I know that much. Maybe 0626927. 0626927. Can't remember. Okay. Good. All right. So I've posted an assignment, but you can try it today. Obviously, you can open up and have a look, but you might have to wait until tomorrow to be able to do it completely. Okay. And so it's there ready for you, but you might have to wait a little bit. Okay. Now what? Now what? Now what? We're going to start 4.1. Which is the normal distribution. Let's see. All right. So the normal distribution, we've seen the shape before, right? So we know the shape of the normal distribution is something like this, or that's kind of weird, but I should make it look good. It's our first one that we're drawing. Hey, that's pretty good. Okay. And so this is the shape of the normal distribution, and a lot of things follow a normal distribution. So when we have numerical measurements, often they will follow a normal distribution. Okay, and so that's why it's going to be kind of core to this whole course is, okay, we got a normal distribution. And so first thing we need to do is just establish some facts about the normal distribution. Okay, so the first thing is that down dead center is the mean. Okay. And the mean is denoted by mu. Okay. So it's for a population. So we're going to use mu for the mean. Okay. So it doesn't really go anywhere, but if we are using the mean as the measure of center, then we're going to use the standard deviation as our measure of spread, right? And so the standard deviation, just remember, is denoted by a lowercase sigma. So what happens here, right? We've kind of seen this before, and we said, okay, well, here around the mean, we have all these kind of common observations, right? We expect things to be hovering around the mean. And then what does it mean when we're sloping down like this, right? Just kind of intuitively, it means that these observations are more rare, right? As you move away from the mean, right, the observations become more and more rare. Okay? So we've got these kind of rare, oops, looks like rave, rare observations in the tail. Now, what am I leveraging here? Well, we haven't said it, but the area under the curve is the probability. Okay? And so the area under the curve I need one more line, is a probability. So when we talk about rare observations, right, they're rare because, right, very few of them happen. And so the probability of being out here is very, very small, right? And so this area is small, and so then the probability is small. Okay? And for that reason, right, hanging out around the mean, the probability is quite high, right? And so then we have a large probability. So the area under the curve is a probability. Now, if you're in the calculus side of things, right, what do you do to find areas under the curve? Integrate. We're not going to do that. Right? But that's where these tables come in, right? And so we don't want to do that. So we'll use tables for that. But I mean, software is doing an approximation at least. Okay, and so if the area under the curve is a probability, then just remembering facts about probabilities, right? The total area under the curve must be 1, right? And so let's add that here. The area under the curve, and I'm kind of repeating myself a little bit, but it is important, so I don't mind. The area under the curve is a probability. So the total area under the curve is 1. As kind of a weird fact, well, it's not weird, but it's mind-boggling a little bit, is that these tails keep going and going and going, and they never actually close on the axis, right? I always draw them closing on the axis because that area becomes very, very small pretty quickly, okay? But in theory, these tails go to negative infinity and positive infinity. And again, we're centered here at mu. Okay. And so here, I'll say kind of the tails go to plus minus infinity, right? there's always kind of reasonable values, but what we're saying is that anything can happen is what that is meant to mean, okay? And so anything can happen. But at some point here, right, the area under the curve becomes very small. Right, and that's in both the tails. So usually we just kind of, we draw it as if it closes, but it never actually closes. So imagine, right, your tails are just lifted off the axes, just, and going all the way to infinity in either direction, but still the total area is 1. So for me, that's kind of, crazy, but that's just how it is. Okay. And so we're going to leverage that fact that we have a total area of 1, and then we'll be able to use the normal distribution to find probabilities. Okay. So what we're going to have is we're going to have some observation, and we're going to denote that observation by x. Okay, so we're going to have some x that we're interested in, a probability that's associated with that x. Okay, so we will be interested in an observation which we will denote by x, a lowercase x. We'll use the normal curve to find probabilities associated with x. We will use the normal distribution to find probabilities associated with x. Okay. Which, like, yeah, I should clean that up. There, a little bit better. Okay. But first, let's deal with some notation. Okay, so first we're going to be told that x, which is just a placeholder for whatever we're talking about, car speeds, for example, times any sort of measurement, really, right? Mosquito lengths, all that kind of stuff, right? We're going to be told that it follows a normal distribution, and then we'll be allowed to use these tools that we're developing now. Okay, so x is going to follow a normal distribution, and we're going to need to know the mean and the standard deviation of that normal distribution. Okay. So x, and yes, confusingly, I will use a capital X, but it's just a general notation for the measurements that we drew a little x from, right? So if I draw one mosquito, then I have a little x, but all the lengths of all mosquitoes come from capital X. Okay, so it's just a group that, and you don't have to worry about it. You can use them interchangeably, and I'm fine with that. But x is the random variable we drew x from, lowercase x from, just to clarify what I just said there. Okay. Oh, I hear someone. Hello? On Zoom, I guess. Maybe it's a question. Maybe. Nope. Maybe I'm hearing things. It's okay. Okay. So we'll be told that X follows a normal distribution. Okay. So we will be told, and by that I mean in the question, that X follows a normal distribution with a mean of mu and a standard deviation of sigma. In shorthand notation, what we can write is instead, or using shorthand, because that's a lot to write, we would say that X follows, and we use a little tilde to denote follows a. Okay. So here, tilde is follows a. Normal distribution, which we denote by a capital N. Okay. And so here, this is shorthand for normal distribution. And then we use a bracket, mu, comma, sigma. Okay. So here with a mean mu and a standard deviation sigma. Okay. So X follows a normal distribution with a mean mu and a standard deviation sigma. It saves you a lot of writing, right? You don't have to write it this way, but some questions will just present the information this way. So then you would need to be able to read it, right? And I think if you look on your formula sheet, here I've used the lowercase x. That was sneaky of me, right? I do have that notation, right? So just be aware. And as long as you know how to read it, that's great. Yeah. Maybe I'll clarify what this is too. With mean mu and standard deviation sigma. Like this? Okay. Yeah. X follows a normal distribution with mean mu and standard deviation sigma. Kind of did it like a sing song there. Read up and down. Okay. So for example, all right, let's do, so for example, if we say that X follows a normal distribution with a mean of 3 and a standard deviation of 1, right? You would read this as X follows a normal distribution with a mean of 3 and a standard deviation, which I'll just write SD, of 1. It's better with numbers. Yeah. One thing to notice is, remember when we were looking at histograms and we said, okay, well, if you have to describe a distribution, right, you have to talk about the shape, you have to talk about the center, and you have to talk about the spread, right? And so now we're just communicating that, right? The shape is normal, the center is 3, and the spread is 1. Okay? And so it is just a shape, center, spread. Okay? One thing that people find really is, well, what's n? I don't know what number to put in for n, right? But just remember, the n is for the shape. Okay, it's for the normal distribution. Yeah.
One, are we allowed to?
Oh yeah, you'll get fresh ones for the quizzes and the test or the final exam. Yeah, so this one is yours to keep, and if you want another one, I've got more. But you'll get a blank one for the quizzes, right? So that one's yours to do whatever with, but then you know what you're heading into the quiz with, right? Okay.
Maybe we didn't get it last year, but I'm looking at binomial distribution, it doesn't
Mm-hmm.
follows. Is that kind of useless?
Where's the binomial?
Right below.
So you could, so the question is about and I'm gonna erase this, but the B and P.
Yeah.
So you could write X follows a binomial. Yeah, it is. But that's for next week. This week, the normal distribution. Okay. So now, what we're gonna do first is we're going to need some way to find the areas under the curves kind of easily, right? And so we know, I've already told you there's a table that we're gonna use, but in order to use that table, what we have to do is we have to standardize our values, okay? And so in order to find areas under the curve, which are probabilities, right? And I'm gonna make a point of saying those two together, and then hopefully I'll just start saying probabilities and your brain will go area under the curve, right? And so I'll say them together for a little bit, but just start linking those two, okay? So in order to find areas under the curve, which are, oops, I should probably start on a fresh line here. Probabilities associated with an observation X we will need to standardize the observation. We will need to standardize the observation. Yeah. So I'm just going to jump right in and say that, okay, well, Z is going to be that standardized value. Okay, so Z is the standardized value. And before I give you the formula, right, let's just think about if I asked you without a formula, right, or you would probably just develop the formula in your mind, but how many standard deviations, so for example, how many standard deviations is an observation of 3 from a mean of 4 if the standard deviation is 1.5. If the standard deviation is 1.5. Uh-oh, I know. I like to use a number line, right? I just like to kind of go like this and I say, okay, so I've got this observation of 3. And I'm gonna jump right in, right? Observations, we're gonna use X to denote. So X is 3, and I wanna know how far is 4. So how many times can I fit 1.5 in here? Uh-oh. Yeah,
don't entirely understand what's means for -3.
Yeah. Yeah, so the distance between them is 1. Right, so the distance is 1. We are standardizing, right? And so what we do when we standardize is we say, okay, well, there's a distance of 1, so that's right, we find that distance. But then I want to see how many times can I fit 1.5 in there, right? And so now I can fit, what we're going to say is Z is the distance divided by the standard deviation. So in this case, that's right. Yeah. 1 over 1.5, who knows? Math, am I right? Yeah, I'm trying to do the fractions. 2 over 3. I trust you guys, but I was already on a roll. 2 over 3, okay, phew. So Z is 2 over 3 or 0.66 repeating. Yeah. Kind of a, if I had numbers that worked out better, that would have been nicer, but that's okay. Right? So what we're gonna say is that, okay, well, we said X is 3 and mu is 4. If we attach some notation to this. So then if I go back up here, then I'm gonna say that X minus mu over sigma, that's how I'm gonna standardize any value of X. Okay. I guess this is really -1, but we didn't include that, right? Why would it be negative? So the distance is 1, but we need some way to denote if it's 1 below or 1 above. And so that's why we always just do X minus mu. And so that way we're gonna get negative values of Z if it's below the mean, right? And so to find the distance, we use X minus mu. So really this would be negative, negative, or negative 0.66, blah, blah, blah. Okay. Because that will ensure that we have negative values of Z if X is below mu and positive values of Z if X is above mu. Okay, so let me just add that here. So because that will ensure, I feel like it's ensure. I'll write my E so it looks kind of like an E and kind of like an I. Sneaky. No, I think it's E, because that will ensure Z is negative when X is below the mean and Z is positive when X is above the mean. So Z is negative when X is below the mean and Z is positive when X is above the mean. Okay. So Z then is the number of standard deviations X is from the mean. So Z is the number of standard deviations X is from the mean. So by standardizing values, not only are we going to be able to use the Z distribution to find probabilities later, but we'll also be able to compare standardized values. So that's where I want to start off here, okay? And so by standardizing values, I'll say observations, which really just means calculating Z scores. And we're going to call them Z scores. I'll just clarify here by calculating Z scores. By standardizing observations, which really means by calculating Z scores, we will be able to compare observations even if they're from different distributions. Okay? So we will be able to compare observations even if they are from different distributions. Let's see, kind of gone rogue a long time ago here, so. But I do want that, there is an example that I want. Okay. So kind of the most common example that we use, oh, we're way past this. Let me just find it here. Yeah, like I said, the most common example that we use is SAT scores and ACT scores. So this is in the States, but kind of high school scores. I don't know what we're doing here anymore. And I don't mean like, I don't know what we're doing. I mean, I actually don't know what our scoring system is anymore in high school, but there's usually kind of provincial exams or something like that. And so in the States, you can write the SATs or the ACTs and apply to universities that way. Okay, so they both measure academic ability. And the thing is, though, that the SAT scores are on one scale and the ACT scores are on a different scale. So I'm going to grab this as well. Okay. So here we have the mean of the SATs is 1,100. Okay. And the standard deviation is 200. So the scores on the SATs are quite large, right? You're expecting large values in order to have done well, right? The ACTs have a mean of 21 and a standard deviation of 6. Okay? And so right now we're expecting these kind of lower scores, especially in comparison, right? And so this example says that, okay, we're given this SAT and ACT information. Okay? The distribution of SAT and ACT scores are both nearly normal. Okay? So what I'm going to do is I'm going to take that information and I'm going to say, okay, I'm going to do them side by side. So what I'm going to encourage you to do a lot of is start by sketching the curve. Okay, so as soon as you see, oh, that was like a worse curve than I started off with. How about that? So as soon as you see that something follows a nearly normal distribution, start by sketching this curve. Okay? And I happen to know I'm going to have one for the SATs and one for the ACTs. Okay? I have the mean and the standard deviations, and so I'm holding off on rating the rest for a little bit. Okay, but what I'm going to do is I'm going to jot down where the mean is, and maybe I shouldn't use such a bright color. The mean for the SATs versus the ACTs. The mean was at 1100. And the ACTs had a mean of, so mu is 21. Now, there are properties of the standard deviation that we'll get to, but in terms of sketching out the information, you're just gonna write it kind of somewhere in there. It doesn't have a line or anything on your curve. I just write it below my mean usually. And so sigma for the SATs is 200 and sigma for the ACTs is 6. So in the question, you would be given all this information, right? It follows a normal distribution with a mean of this and a standard deviation of this. So now we're ready to tackle this problem. Suppose Anne scored 1,300 on her SAT. Okay, so she wrote the SAT and she got a score of 1,300. And Tom scored 24 on his ACT. Okay, so Tom wrote the ACT. So here, what I'm gonna do is I'm gonna say, okay, one thing to remember is that this lower axis here is just the number line, right? And we're only sketching the curve to visualize what we're trying to solve. So it doesn't have to be perfect or anything like that. The only key information that I need to communicate here is that 1,300 is above 1,100, right? And so where I put it, it doesn't actually really matter. I'm gonna put it here. Okay. And so how I'm gonna denote this is I'm gonna have X, because that's the observation that I wanna talk about, right? And a little bit overkill, but I'm gonna do a little subscript and on here just to say, to remind myself that this is Anne's score, and that score was 1,300. I'm gonna do the same thing for Tom. Again, it's really important that 24 is placed above 21, but besides that, you know, you just kind of wanna give yourself room so you can see where it is, okay? But so I'm gonna say, okay, X for Tom was 24. Okay. Just to practice that normal notation, right? We could say that the SAT scores follow a normal distribution with a mean of, oops, forgot, 1,100 and a standard deviation of 200. And ACT scores follow a normal distribution centered on 21 with a standard deviation of 6. Right, that's just to practice that notation and just to see it with the drawing too. Okay, so who performed better? What do you have to do? You're gonna have to standardize both those scores, right? You wanna see how many standard deviations above the mean was Anne and how many standard deviations above the mean was Tom relative to their distributions, right? And so I'll write it out, but I'll let you guys work through that and then we'll talk it through. Yeah. So remember, you're gonna use, and then I can't stop talking, Z for Anne. I'm just gonna set up the first one. Z for Anne, and the subscripts that I'm using are really just to kind of, one, get into the habit of using subscripts, but also to keep Anne and Tom separated. Okay? And so here, X for Anne, oops, no, minus mu over sigma. There, now I'll clam it. and just do it. Okay. So what? Oh, sorry. Yes. And I know it looks weird to write it with 3 decimal places, but later we're going to need it to at least 3 decimal places. And so I just want to get you guys in kind of good habits right away, right? Of course, 1.000, you can just 1, right? That's totally fine. But when we're using the table, we're going to need at least 3 decimal places. So that's why I'm kind of pushing you towards 3 decimal places. Okay. So here, note, later when we use the table, we will, forgot the we, which happens a lot. We will require at least 3 decimal places. So it's just good to get in that habit. Unnecessary here, but it's just for show. All right. So we did our calculations, right? Remembering that we first do the X, so the observation minus the mean, and that'll force a positive if X is above the mean and a negative if it's below, right? Because that's important information, right? If this was -1, it would mean that Anne's score was 1 standard deviation below the mean, right? But here she's 1 standard deviation above the mean, right? Whereas Tom was half a standard deviation above his mean, right? Which means he didn't perform as well as Anne did relative to their own distributions, right? So I'm going to write out that in words here. So Z for Anne equal to 1, I'll do like that. Means Anne scored 1 standard deviation above the mean. And Z for Tom was I almost inserted a 0 in again, right? 0.5, okay? Which means that Tom scored half a standard deviation above the mean. Means Tom scored half a standard deviation above the mean. Which means what? So now we can say, therefore, Anne performed better. Go Anne. Okay. Nice. Mm. Okay.
Emily,
Trying to think of. Oh, hello.
so yeah, I have a question.
Yes.
So basically, Z score means it basically is standardizing the value between different distributions, right?
That's right.
So when the two distributions are totally different with each other, but Z score standardizes two different distribution so that we can compare both of the distributions, right?
That's right.
Okay.
Yeah. Good. Okay. Nice. So the Z scores, we use them to standardize values. Once we have standardized the values, then we'll be able to find probabilities. Okay. So once we have standardized the value, I'll say an observation. And just to emphasize, we denote that observation by X. So once we've standardized an observation X, we will now be able to find probabilities associated with X. We will now be able to find probabilities associated with X. Okay. How are we going to do that? What do you guys want to learn first? Do you want to use the software to find? So the difference between the software and the table is that the table is going to give you just an approximate range. It's not going to give you the value exactly. It's just going to give you a range of values and the probabilities somewhere in here. Whereas the software, I'm leaning towards just introducing the software right away because it'll give us a value. Okay, fine, done deal. Software first. I had to talk myself into it. Oh boy. Okay. And so I'll kind of summarize that here. To find exact probabilities, we use software. So in our case, I'm going to use R. But I mean, Excel does it too. You can find online calculators that do it, but any sort of software is fine. So I'm going to show you how to use R, but there's equivalent functions in Excel that are going to give you the same values, maybe more or less decimal places is all. Okay, so to find the exact probabilities, we use software. Or to find approximate probabilities, we will use a t-table, is what it's called. It's because it's a distribution of t's, but there is a z-table, of course, it's out there, but I don't want to use it because it's old school. It's too old school for me. I don't want to. And you shouldn't have to. Okay. So what we're going to have is we're going to have a question like the one we just solved. Okay. So here we answered who performed better. We were able to answer that with just the Z scores. Now, what if I asked a follow-up question like what proportion of SAT writers had a better score than Anne, right? That could be something that we would want to know. Okay, so for example, what proportion of SAT writers had a better score than Anne? So we already drew the distribution for the SATs. Well, it's not very nice, but we said the mean was 1100. The standard deviation was 200. And we said that somewhere here is Anne, and she had a score of 1300. The proportion, remember the 3 Ps, proportions, probabilities, percentages, right? So those are all going to be areas under the curve. So this is really just area under the curve, right? But we have 2 areas under the curve. We have an area to the left and we have an area to the right. Okay. And so now we want to match the area to what we want to find. So had a better score than Anne. So what we're going to do is we're going to shade the area that we're interested in. Okay. So here, this area is the proportion with scores better than Anne. What's the opposite area? That would be the proportion with scores less than Anne, right? We could find that as well, but I'm starting out with a big example. Okay. So in R, or first, let's recall that Z for Anne was 1. Right, we already did that. Okay. But like I said, we're going to need these standardized scores to find probabilities. I'll show you a sneaky way that you don't have to do it, but to start off with, right, I want to see those Z scores, and to use the table, we'll need the Z scores anyways. Okay, so in R, bless you, you're going to write, there's a P norm command. So it's, the P stands for probability, I think, and the norm just is the normal distribution. Okay, so the P norm command takes a Z value. Okay, so it's going to look like this, and this returns the area to the left of the Z that you entered. And it's really important that you remember that it's to the left. So it'll only give you the area to the left, right? But that's okay. Why? Because we also know that the total area is 1, right? And so we can use that. If I know the area to the left and I know the total area is 1, I'm left with a little puzzle piece there, right? And so returns the area to the left of Z. Okay, so I'm going to boot up my RStudio here. Sorry, pause it. I have 1.23, so I was surprised when it was still logged in. It wants to log in every time. Like I said, main complaint is how slow it is. But it's nice because you can have it on your iPad, so. Because you can't install R in RStudio on your iPad.
What will like be our usage on the left and right side?
Yeah, just on the assignments, but on the tests, just the table
Oh, okay.
or quizzes. Yeah. So you'll have this table in the quizzes, but I just want you to be able to find them properly as well, not just because we're limited to paper quizzes, right? So, so I actually did my tests on a computer last term for Stat 230, but the dean's office didn't like it. So I got in trouble. So we're back to paper. We're getting there. We're getting there. But kind of fun because I was completely paperless last term. I think that's impressive, right? Not all these tables. Well, I did print the formula sheets. Okay, so when you're working in R, just some basics about R here is you can write a little comment to yourself using yeah, it's a hashtag, it's a pound sign, but its proper name is an octothorpe. Thank you. Anyways, right, it's octothorpe. Yeah. 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 Who knows? It's like trivia. Anyways, so a hashtag, you can write a little comment to yourself. And I posted this R script on Moodle, so if you want to, you can grab it, just copy and paste because there's not a lot in there. And so what I have is we can find the area to the left of, I just picked Z equals 1.23, 123, using that P norm command. So then I put in P norm of 1.23, right? And then because I'm on the iPad, it's just easier if I have my cursor somewhere on the line that I want to run, and then you hit that run button up top there. What's going to happen when I do that is it bumps it down into the console. So this is where R is, and this is the brain that we are using. So it's basically just a huge calculator. You can do things like calculate Z, right? Even in here. Now it's kind of hard, I guess. Ooh, tiny keyboard. If I did something like that calculation that we just did. Man, this is hard. Okay. 1300 minus 1100. Divide that by 200. Oops, 209. Oh. Why is it still thinking? It took a long time to get to 1. Anyways, so that's okay. So now what you can do, you can kind of build out from here. You can store that in something called Z and then use that value, or we can do just in the console if you want to. The problem is when you write just in the console here, it disappears later when you close it, right? So if you want to save it, you write it in a script, and then you'll be able to pull it up and just run it again, okay? And so, like I said, not on the test, but it is, these are life skills. So the P norm of 1, enter, is 0.841347. So I'm going to screenshot this and bring it in so we can talk about it. Maybe not all of it, because it'll be huge. Okay, so here, we were given Paste. We were given that this area, which color can I use? This area here, right? Remember, it only gives the area to the left. This area is 0.8. And sometimes what I do to show it, because sometimes it can get a little bit messy, I draw a line up from where I want it to be, and then I draw a line going all the way over. And then I write the area underneath or over top, maybe, I don't know, 0.841347. Leveraging the fact that the total area is 1 means that this area is 1 minus 0.8413447. I'm gonna, oh, now I get a big keyboard. So now I'm just gonna do 1 minus p norm of 1, return. And that's the same, right, as just doing it on your calculator, but I'm using this as my calculator because I'm cool like that. Maybe I'll put it here. How about that? So it is 0.1586553. Oops. It depends on how it was asked. So I can't remember if I asked, yeah, so what proportion? So then just leave it as a proportion. But I could have asked what percentage of SAT writers, and then you would convert it. Sometimes the assignments are clever enough to accept both. So it'll be okay with either or, but if it's complaining, then just make sure that you have it in the right format. Okay, nice. So now let's use the table instead, or I guess I should. Therefore, 0.1586553 of SAT writers had a better score than Anne. Now using the t-table instead, because I do want to introduce it today, using the t-table to find approximate proportions, probability. First, let's bring in that t-table. Oh, I don't have it here yet. Oh. Ooh, what a mess. I think I kept it up there, but there is a Z table. So if you wanted to test out the Z table, you can, but it's 2 pages and it just is a bunch of numbers and we don't actually need it. We're gonna use this little guy. Okay, so the table that you have, it looks like this. I'm gonna just grab the first 2 rows for now. Okay. And the bottom 2 rows. in chapter 6, I think it is, we're gonna start working with t's. That's when we'll start using the rest of the body here. I want it to line up there. Okay. So here, what we're interested in is we're gonna use this in a bit. We're gonna use this Z star row. Okay. And potentially either one of those. I'll show you what they both mean. Okay. But our focus here is going to be on the Z star. So that's our Z row. Okay. And everything else for now, just ignore for now, especially in these degrees of freedom as well. They don't mean anything to us right now. Okay. So one thing that you're going to notice is that, okay, these are just Z scores. Okay. And one thing that we're leveraging is that Z is symmetric around 0. Okay. And so Z buckle up, Z follows a normal distribution with a mean of 0 and a standard deviation of 1. And that's just a fact. Okay. So therefore, Z is symmetric about 0. Okay. So what we're going to have is we're going to have this normal distribution centered on 0. Okay. And then these are just kind of check-in points for Z. And remembering that this lower axis here is just the number line, right? And so what we have is we're given, okay, 0.674, 841, and then kind of keep going a little bit, 2.576, for example. So I'm just grabbing some of these. There's not enough room to have them all on one graph, especially when I draw it so tiny. Okay. But these are just little check-in points. Okay. And what it's telling us is that the area in the tail, okay, which from 0.674, the area in the tail is 0.25. Okay. So looking at the one-sided P is where I'm going to focus. So here, if I draw up, then this area is 0.25. That's the one-sided P for Z equal to 0.674. Okay. Can do the same thing for 0.841. That's the next one. The area in the tail for 0.841 is 0.20. So again, one-sided P. And then I skipped a bunch and I went to 2.576. And the area in the tail then is 0.005. There's a reason we're going on and on about these areas in the tails, because later when we do hypothesis testing, we'll want to know what's the probability of seeing something more extreme, right? More extreme is going to be the area in the tail. So we're just building up towards that. Okay. By symmetry, okay, and so this is the important part, is by symmetry, we know that at negative 0.674, right? So now I'm just by symmetry around 0. We don't need the negative values, right? Because I can just make it negative and then flip it to the negative side here, but then I know that this area in the tail is also 0.25. Yeah. Which is where the two-sided P comes from. Right now, if I look in the area of both the tails together, it's 0.5, 0.25, and 0.25 makes 0.5. So you don't really need the two-sided P, right? It's just there because why not? Okay. Same thing here. If you have negative 0.841 and negative 2.576, the area in the tail 0.20 and 0.005. And it's not on there, but it is important to remember that the mean splits it in half, right? Which means the area here is 0.5 and 0.5. And I'm gonna just give myself just one more line. Right, so here at the mean, you're at 0.5 and 0.5. I know I'm out of time, but just to get you grooving, how we use this, I take the Z that I calculated, right? Z of 1. 1 is between 0.841 and 1.036, okay? And so then the area in the tail is somewhere between 0.1 and 0.15. Notice that as you move out into the tail, the area in the tail becomes smaller as Z increases. So it makes it a little bit hard to communicate. I will talk about this tomorrow, but Z for Anne is 1.000, which is between 0.841 and 1.036 on the table. I think it was 1.036. Copy. Okay. So it's somewhere between here and here. So what I do is I write the one-sided P, or the area in the tail, or the probability or the proportion, is going to be somewhere between 0.15 and 0.20. Notice that we have to write them in ascending order, or you can flip the inequalities, but I don't like to do that because I hate inequalities and I don't want to think about it. So for me, I prefer to just flip these values around when I read it, right? Read it from right to left. But it depends on your relationship with inequalities. So I'll talk about that again tomorrow, but that's how we're going to use the table. And notice, last thing, between 0.15 and 0.20, well, we found it was 0.16 or 1.16-ish, which is awesome. Good job, guys. All right, let me know if you have any questions, but I'm going to stop this recording.